Welcome to our Bioprocess Engineering online tutorial on microbial fermentations optimization criteria. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. The scale-up of fermentation processes, which rely on microbial cells such as bacteria, yeasts, and fungi to produce a wide range of valuable products, is a fundamental challenge in bioprocess engineering. A primary objective of scale-up is to identify and establish operating conditions that ensure optimal fermenter performance at large industrial scales. In this introductory tutorial on the optimization of microbial fermentations, we will address the following questions. How can microbial fermentations be optimized? Which economic criteria should be considered in an optimization strategy? Which technical criteria underlie these economic objectives? What are the relationships between technical and economic optimization criteria? When optimizing a microbial fermentation, the first step is to select the most appropriate mode of operation. Depending on the process objectives and constraints, the optimal choice may be batch, fed batch, or continuous operation. In batch fermentation, the fermenter is filled with the entire volume of medium at the start of the process, and no medium is added during cultivation. In fed batch fermentation, only part of the medium is introduced initially, and the remaining portion is added progressively throughout the fermentation to control nutrient availability, growth rate, or product formation. In continuous fermentation, fresh medium is continuously supplied to the fermenter, while an equal amount of fermentation broth is simultaneously withdrawn, maintaining a constant working volume in steady-state operating conditions. For a selected mode of operation of the fermenter, the next step is to determine the optimal operational variables. These typically include the concentrations of substrates or nutrients in the medium, the medium flow rate for fed batch or continuous processes, the fermenter aeration rate, the timing of metabolite induction for inducible production systems, and the final fermentation time or harvest point. When a microbial fermentation is carried out in a fermenter, the selected mode of operation together with the chosen operating variables determine the fermentation kinetics, that is, the time-dependent evolution of substrate, biomass, and metabolite concentrations. The central question then becomes, which criteria should be derived from these kinetics to evaluate the performance of the fermentation process? In other words, which quantitative criteria should be used as a basis for optimizing the fermentation operation? The primary optimization criterion of a fermentation process is economic. In most cases, the operation is optimized to achieve the lowest possible production cost of the target product. Reducing production costs enhances the economic competitiveness of the fermentation process and improves its viability at industrial scale. The general methodology for bioprocess cost evaluation is described in an earlier tutorial. The fermentation cost includes all expenses associated with materials, energy, equipment use, and labor. Material costs cover the nutrients supplied in the medium, primarily carbon and nitrogen sources, as well as water and any additional supplements. Energy costs arise from fermenter agitation, aeration, cooling, and fluid pumping. Equipment costs include capital depreciation, maintenance, and other expenses related to equipment utilization. Labor costs comprise the salaries of technicians and supervisors or engineers, along with general overhead costs borne by the company. For an annually operated process, the total annual cost corresponds to the combined annual expenditures for materials, equipment, energy, and labor. The annual production cost of product P, which is either the biomass or a metabolite, or a recombinant protein, is denoted as euros P annual. The key economic criterion for fermentation optimization is the production cost per kilogram of product. This unit cost is obtained by dividing the total annual production cost by the corresponding amount of product generated over that year. Accordingly, the production cost per kilogram product is equal to the sum of the material, equipment, energy, and labor contributions, expressed on a per kilogram basis. It is this unit production cost that the fermentation optimization strategy seeks to minimize. Cost optimization of a fermentation process is driven by the optimization of two underlying technical criteria. The most important technical criterion is the fermentation productivity, which integrates both the product concentration and the total fermentation time. High productivity generally leads to lower production costs by improving fermenter utilization. Another essential technical criterion is the substrate to product conversion yield, which reflects how efficiently raw materials are converted into the desired product and therefore directly affects material costs. Note that the achieved final product concentration is not a key criterion for the fermentation operation. It influences the fermenter productivity and substrate conversion yield. It also governs the efficiency of the downstream product recovery and purification operation. The main technical criterion is the fermenter productivity, denoted ProdP, and typically expressed in gram P per liter an hour or kilogram P per cubic meter an hour. For a year-round fermentation process, productivity is calculated by dividing the annual mass of product, MPN, by the fermenter's useful volume, VF, and the annual operating time, TN. Fermenter productivity represents the average volumetric production rate achieved over the full operating period. It is therefore a direct indicator of fermenter utilization efficiency, reflecting how effectively the installed fermenter capacity is converted into product over time. How to increase the productivity of a fermentation? Fermentation productivity can be improved through two main approaches. The first approach is to increase the final product concentration at the end of the fermentation. This can be achieved by increasing the concentration of substrates in the culture medium, in particular the carbon source, provided that substrate inhibition or byproduct formation remain under control. The second approach is to reduce the process duration. In batch fermentations, this corresponds to shortening the fermentation time, while in continuous systems, it involves decreasing the residence time. Shorter process times increase productivity by allowing more production cycles per year or a higher throughput. This intensification of the process is mainly achieved by increasing the biomass concentration during fermentation, which enhances the overall rate of product formation. The second key technical criterion is the substrate to product conversion yield, denoted as YP over S, in gram product produced per gram substrate utilized. Since the carbon source, often a sugar, is typically the largest contributor to material costs, this criterion is usually expressed as the sugar to product yield, measured in grams of product per gram of sugar supplied to the fermenter. This yield is calculated by dividing the mass of product obtained at the end of fermentation by the mass of carbon substrate added during the fermentation. YP over S equals MPF over MSF. The same definition applies on an annual basis as the ratio of the annual mass of product generated to the annual mass of substrate used. Thus, the global conversion yield quantifies the efficiency with which the fermenter converts substrate into product, directly linking biological performance to material cost. How to increase the sugar-to-product conversion yield? The sugar-to-product conversion yield is primarily governed by the metabolic behavior of the microbial cells during fermentation. That is, by how efficiently the consumed sugar is directed toward the desired product rather than toward byproducts or cellular maintenance. The lower the formation of unwanted metabolites, the higher the achievable conversion yield. This can often be promoted by operating at lower substrate concentrations, which helps to limit overflow metabolism and byproduct formation. The conversion yield also depends on the extent of substrate utilization at the end of the fermentation. More complete consumption of the available carbon source generally results in a higher sugar-to-product conversion yield. This can be achieved by appropriately controlling substrate concentrations in the medium and ensuring that fermentation conditions allow near-complete substrate depletion without inhibiting cell activity. The two technical criteria, fermenter productivity and substrate-to-product conversion yield, directly determine the production cost of fermentation per kilogram of product. The unit production cost can be expressed as a function of these two criteria, since they govern how efficiently the fermenter volume and raw materials are utilized. In this section, we analyze how each technical criterion influences the four major components of fermentation cost: materials, equipment, energy, and labor. When sugar represents the dominant contribution to the material cost, the sugar cost per kilogram of product, euros S per kilogram P, is obtained by dividing the annual sugar cost, euros S N, by the annual product mass, kilograms PMPN. The annual sugar cost is the product of the annual mass of consumed sugar, MSN, and the unit sugar price, in euros per kilogram S. The sugar cost per kilogram of product can therefore be expressed as the unit sugar cost, divided by the ratio of the annual product mass to the annual sugar consumption mass, which corresponds to the substrate-to-product conversion yield, YP over S. Thus, the sugar cost per kilogram of product is inversely proportional to the conversion yield YP over S, euros S per kilogram P, equals euros S per kilogram S, divided by YP over S. As the substrate-to-product conversion yield increases, the sugar cost per kilogram of product decreases. A more detailed evaluation of the material cost includes the contributions of other substrates and nutrients in addition to sugar. This can be accounted for by introducing the fraction of sugar cost in the total material cost, denoted as percentage euros S over euros mat, which is typically 80 to 90% for many industrial fermentations. Accordingly, the material cost per kilogram of product euros mat per kilogram P can be calculated by dividing the sugar cost per kilogram of product by this fraction. Euros mat per kilogram P equals euros S per kilogram P divided by percentage euros S over euros mat. By combining with the previous relation for euros S per kilogram P, euros mat per kilogram P equals 1 over percentage euros S over euros mat, euros S per kilogram S, divided by YP over S. The equipment cost per kilogram product, euros equip per kilogram P, is the annual equipment cost, euros equip N, divided by the annual mass of product, MPN. During the year-round operation, the annual production of P is related to the fermenter productivity ProdP by the relation MPN equals ProdP VF TN. Thus, euros equip per kilogram P equals euros equip N divided by ProdP VF TN. It is useful to define the cost of the fermenter utilization per cubic meter of fermenter and per hour, noted euros equip per cubic meter an hour. This value is obtained by dividing the annual equipment cost, euros equip N, by the fermenter volume VF, and by the annual time of operation Tn. The equipment cost per kilogram product can be written simply as fermenter utilization cost per cubic meter an hour, divided by the fermenter productivity. Equipment cost per kilogram product is inversely proportional to the fermentation productivity. Hence, increasing fermenter productivity directly reduces the equipment cost per kilogram of product by improving the efficiency of fermenter utilization. The energy cost per kilogram of product, euro-ener per kilogram P, is obtained by dividing the annual energy cost by the annual mass of product produced. During year-round operation, the annual product mass, NPN, is related to the fermenter productivity by MP on equals ProdP VF T on. Thus, the energy cost per kilogram of product is euros Nr per kilogram P equals euros Nr on divided by ProdP VF T on. We can define the energy utilization cost per cubic meter of fermenter an hour. It is calculated by dividing the annual energy cost, euros Nr an, by the fermenter volume VF, and by the annual time of operation Tn. The energy cost per kilogram product can be written simply as the energy cost per cubic meter an hour divided by the fermenter productivity. Thus, as productivity increases, the energy cost per kilogram of product decreases since the same energy expenditure supports a greater product output. A similar approach applies to the labor cost contribution per kilogram of product. The labor cost per kilogram of product is obtained by dividing the annual labor cost by the annual mass of product produced, expressed as euros lab per kilogram P equals euros lab an, divided by prod P VF T an. We can define the labor utilization cost per cubic meter of fermenter per hour by dividing the annual labor cost by the fermenter volume VF and the annual operating time Tn. The labor cost per kilogram of product therefore becomes labor cost per cubic meter an hour divided by the fermenter productivity. Thus, as fermenter productivity increases, the labor cost per kilogram of product decreases because a larger product output is generated for the same labor expenditure. The total production cost per kilogram of product is the sum of the four contributions from materials, equipment, energy, and labor. Because each of these contributions depends on either the fermenter productivity or the substrate to product conversion yield, the overall production cost is directly determined by these two technical criteria. Accordingly, the lowest possible production cost is achieved when the fermenter operates under conditions that simultaneously maximize productivity and maximize substrate to product conversion yield. In microbial fermentations, however, the conditions that yield the highest productivity can differ from those that maximize conversion yield. As a result, the optimal fermenter operation represents an economic compromise between these two objectives. The fermentation optimization strategy, based on technical and economic criteria, is illustrated on the example of the glutamic acid fermentation. The fermentation is carried out by a Corynebacterium glutamicum strain. Glutamate excretion is induced by temperature increase, for instance from 33 to 39 degrees Celsius. A typical batch fermentation is performed on an initial 200 grams per liter sugar, for an induction time at 4 hours, and a final fermentation time of 36 hours. The batch fermentation yields 8 grams per liter biomass, 105 grams per liter glutamate, and 25 grams per liter trehalose. The glutamic acid fermentation is carried out in an industrial 200 cubic meter fermenter operated in consecutive batch mode throughout the year. This production scheme yields an annual output of approximately 3,600 tons of glutamate, considering only the fermentation step, excluding upstream and downstream operations. The annual operating cost is about 8 million euros. The main cost contributions are as follows. Raw materials, 60% of the total cost, with sugar accounting for 90% or more of this category. Equipment utilization, 15%. Energy, 7%. Labor, 17%. The production cost of glutamic acid per kilogram of product is evaluated using the four-term cost model, which includes the material, equipment, energy, and labor costs per kilogram of product. This cost can be expressed as a function of the two key technical criteria, fermenter productivity and sugar conversion yield into glutamate. In this evaluation, the following unit costs are used: sugar cost, 0.6 euros per kilogram. Equipment utilization cost, 0.74 euros per cubic meter an hour. Energy cost, 0.37 euros per cubic meter an hour. Labor cost, 0.86 euros per cubic meter an hour. For the batch fermentation considered previously, the two technical criteria are fermenter productivity, 2.4 grams per liter hour, or 2.4 kilograms per cubic meter hour. Sugar to glutamate conversion yield, 0.52 gram glutamate per gram sugar. Using these values, the total production cost is 2.1 euros per kilogram of glutamate. When the temperature shift timing is optimized to achieve the highest biomass concentration permitted by the fermenter's oxygen transfer capacity, the batch characteristics become the following. Delayed induction time at 4.8 hours. Higher final biomass concentration, 11 grams per liter. Similar final product concentrations, 100 grams per liter glutamate and 25 grams per liter trehalose. Shorter total fermentation time, 26 hours. As a result, the fermentation productivity increases from 2.4 to 2.9 grams per liter hour. The sugar conversion yield decreases slightly from 0.52 to 0.5 gram glutamate per gram sugar due to increased biomass formation. Because of the increased productivity, the production cost of glutamate is reduced from 2.1 to around 2.0 euros per kilogram. The glutamic acid process is further improved by switching to fed batch operation. In this mode, the sugar feed rate is adjusted to maintain the glucose concentration at approximately 10 grams per liter, thereby limiting trehalose excretion. For the fed batch fermentation, the key characteristics are induction time at 5.9 hours, final biomass concentration, 11 grams per liter, final glutamate concentration, reduced to 90 grams per liter, trehalose concentration, negligible around 1 gram per liter. Under these conditions, the productivity decreases slightly from 2.9 to 2.8 grams per liter hour. The sugar conversion yield increases strongly from 0.52 to 0.56 grams glutamate per gram sugar, primarily due to reduced trehalose formation. As a consequence, the glutamate production cost decreases to 1.88 euros per kilogram. In this introductory tutorial on microbial fermentation optimization criteria, you learn that process optimization relies on two major technical criteria. One, fermenter productivity, ProdP, defined as the annual mass of product produced, divided by the fermenter volume, and the annual operating time. Two, substrate conversion yield into product, YP over S, defined as the annual mass of product produced, divided by the annual mass of substrate consumed, particularly the sugar carbon source. These two technical criteria directly determine the key economic criterion, the production cost per kilogram of product. Maximizing the substrate conversion yield reduces the material cost. Maximizing fermenter productivity reduces the equipment, energy, and labor costs per kilogram of product. Consequently, optimal fermentation operation requires balancing these two criteria to achieve the lowest overall production costs. Beyond economic objectives, industrial optimization may also consider additional factors related to product quality, process robustness, operational risks, and safety requirements. If interested, you can gain a deeper insight in microbial fermentations process optimization by enrolling to one of our two online courses, Simulation, Scale-Up and Optimization of Microbial Fermentations, and Digital Scale-Up and Optimization of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering. And be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.